Hi everyone, this is a quick tutorial video to give you a bit of an idea about how to use the debugging capability inside MPLAB to troubleshoot your AVR hardware projects. Now, a debugger is basically a bit of functionality that's built into a development environment that allows you to pause a program that you've written while it's executing. So you can actually freeze the program at a particular point and then just click a button and go step by step through your program. And then you can do things like creating what are called watch points to look at variable values. And you can also, as is the case with the AVR, you can actually run your debugger on the actual chip. And so MPLAB contains two ways to debug code. One is using what's called the simulator, where the MPLAB software itself simulates running on an AVR, but you don't actually run on a real AVR. The other type of debugging is called in-circuit or sometimes on-target debugging, where the code is actually downloaded into your AVR chip and is running on your AVR chip, but through the Snap programmer, you stay connected to MPLAB and you can halt the program running on the actual AVR chip and then step through it step by step. And I'm going to show you this in-circuit debugging because I think it's most helpful for getting through the labs and the ENEL 300 design project. Running the simulator is good, and we're going to actually be using it in the lectures when we look at assembly language. But this is a little bit better, especially because then it allows you to test, your LEDs and switches and how they're working, as interfaced to your chip. Okay, so let's take a little bit of a look at this program I've got here. So this is a very simple program. It configures PA5 as an output pin. We've got a couple dummy variables here called some math and more math. And then we enter our while loop. And we have a line here that turns the LED on. Then we do a little bit of math. This is just a kind of a garbage calculation just to be a placeholder. Then we turn the LED off, and then we do a little bit more math, and then we loop back and we turn the LED on, off, on, off, and so on. And this is going to be the program that I'm going to use as my debugging demo. Now, if we we know already now from our experience with the labs that basically when you're in this while loop, the AVR microcontroller is going to burn through this loop as fast as it possibly can. It's going to turn the LED on, it's going to increment this variable, turn it off, double this variable, loop back, and then repeat again as fast as its clock is going to allow this to happen. And so basically the LED is just going to flicker on and off really, really fast. And it's going to be so fast that it's basically going to look like the LED is essentially on, but perhaps slightly dimmer. And so I'll just show, I'll demo this first. Okay, so I'm just going to build and program the AVR chip. Program verify complete. And if we take a look at our circuit, I'll find something to point with here. If we take a look at our circuit, this is our LED in question. And as I said, it basically just looks like it's continuously on. But in this while loop, we're just sort of burning through it as quick as possible. The LED is flickering on and off, but the clock is running so fast that it essentially looks like it's continuously on. Now, what I'm going to do next is sort of explain a little bit about the debugger, and we're going to freeze the program, and we're basically going to step through it by pressing a button, and then we're going to see how that slows down the LED. Okay, so in order to use the debugging capability, we've got to change some of the the properties of our compiler. We've got to change our compiler settings. So this project I'm calling debug demo. And so I'm going to right click on it, go down to properties, and you have to go into XC8 compiler, choose optimizations, and probably by default this is going to look like this, right? Optimization level is going to be 1, and this little debug block is going to be clicked off. You have to turn the debug option on and then put the optimization level down to 0. This is because optimization, kind of by its code optimization by its nature, sort of tries to do clever things, and even if you write a very sort of redundant, kind of inefficient program, it's going to try to make the resulting assembly language more efficient. And so the assembly language might not necessarily directly map back to each one of the C statements in your program. And that makes debugging kind of hard to do. So if we set this down to 0, the assembly language that's produced by the compiler will be a relatively one-to-one match with your C code, and that's going to make debugging just work a little bit better. So we click on Apply, click on OK, and the next thing we want to do is we want to create what are called breakpoints. And you can create a breakpoint just by clicking on the line number over here. And if you created a breakpoint, you get this little square, and then it highlights the line in red. And I'm going to create a breakpoint at the dir set command. I'm going to create another breakpoint down here at the command that is where we turn the LED on. Really important that you hit the clean and build button here, not just the build button and not just the load button. We need to clean the project because when you compile with debugging support, a bunch of extra code is added to your executable, and we need to make sure that that goes in there. So clean and build. And now I'm going to take a look at the circuit again, and then we'll start the debugging. Okay, so if you want to debug, rather than hitting the little make and program device button, we're going to travel over here to this debug main project button and hit that. And then you're going to see some messages down here. And a bunch of stuff kind of happens all at once. So first of all, up here, you see this little green arrow next to the this first line of code where we put our first breakpoint. That means that the program is actually paused at this line of code. So it's not executing, the program is paused. And you'll see what's happened to our LED. Our LED has gone out because we haven't yet reached the part of the code that turns the LED on. Now, in addition to this pausing, we see we've got a bunch of other buttons here that have shown up in MPLAB. This continue button that looks like a play button. You basically, if you hit continue, that means the program starts to run as normal until it encounters another breakpoint. There's also some other buttons called step over, step into, step out, and then run to cursor, and a few other ones. The main one that we're interested in is step into, F7. This basically is going to allow us to step ahead in our program. Now, what I'm going to do, first of all, is I'm going to hit the continue button so we see how that works. So we're going to hit continue, and we jump ahead to our next breakpoint. This is what has turned the LED on, and now you can see the LED has turned on. So what I want to do next is just step ahead one step in the program. So I'm going to hit the step into button, and we jump ahead to the line where we turn the LED off. You'll notice that we skipped over this sum math plus plus line. Ideally, our debugger would allow us to step through every single one of our lines of code, but the debugging capability in MPLAB isn't great. So the way, even with optimization turned off, even with debugging turned on, the mapping between C and the assembly language isn't direct. And so, as we're going to see later on when we start to write assembly language, this step into command really, works very well when we're moving from one assembly language instruction to another, but it tends to skip over some of the C lines, which isn't amazing, but this is still better than nothing. If we hit the step into button again, we jump back up to the statement for turning the LED on. We haven't yet turned the LED on because it just pauses here. So we pause here, and before this, so when we're on this line, it means we haven't yet executed this line. When we hit the step command again, the LED goes on. It hasn't turned off because we've paused on the turn off line, but we haven't actually executed this line yet. So when we hit step, the LED goes off and on, and so on. And so you can see this is useful, right? Especially for, for example, the, part C in Lab 1, where, people had a lot of kind of logic inside their programs, and it's kind of nice to be able to understand how the thing would actually be tracing through the logic in your program. This debugger is basically the way to do something like that. It's unfortunate that we don't step through every single line of C code, but generally speaking, I find that the debugger does a good job at pausing on at least the special function register statements. That seems to be pretty consistent. So as long as you put your breakpoints on special function register statements, and as long as you've got special function register sort of commands to step to, then this tends to work pretty well. So once you're finished debugging your program, you can just hit this little stop button, and our green arrow goes away, and we're no longer executing our code on the AVR. Another one of these limitations, like I said, the debugger tends to pretty reliably stop on these special function register lines of code. Regular C code is less consistent. So for example, if I tried to put a breakpoint at some math ++ and then built and ran the debugger, we're going to get an error here that says broken breakpoint. A broken breakpoint is basically happens when the compiler is not able to map a C statement directly down to an assembly language statement. So the sum math ++ statement is not just a single line of assembly code. It's going to be a little cluster of assembly language commands. And, for whatever reason, MPLAB is not great at mapping, at just choosing one of those assembly language commands and, pausing at that particular point. So it's a limitation of MPLAB, unfortunately. Happily, there is a little bit of a hack that you can put into your code to help the admittedly somewhat less than dazzling debugging capabilities of MPLAB sort of along. So include AVR CPU func.h, and if there's a particular part of the code that you definitely want to put a breakpoint at, or you definitely want to hit when you hit the the little step button, you can put what's called a no-op command, and it's _NOP semicolon. A no-op command is an assembly language. This no-op statement maps directly to a single assembly language command, and that command is the no-op command. So all assembly language instruction set architectures have a no-op command, and it's basically a dummy command. It's a command that just feeds through the CPU, and the opcode just tells the CPU to do nothing at all. And it's essentially a placeholder, but it does allow us to, because it's so easy to map this no-op directly to a single line of assembly code, you can always really reliably add a breakpoint wherever you have a no-op. So if you make, and then if we debug, you'll see that sure enough, our breakpoint worked just fine. It stopped at the no-op. If we hit the step into, we're still going to stop at our special function registers, but oops, we're also going to stop at the no-op command as well, right? So now we're stopping in 3 places in the code. And so you can sort of sprinkle these no-ops throughout your code, and that will just reliably be sort of a landing point either for a breakpoint, or if you just want to use the step button will always reliably land at the no-op. If you put a no-op in a little bit of code and it doesn't end up landing there, it's probably because there's a bug in your code that's preventing from that part of your software from being executed. So anyways, I hope you found this helpful. It's a little bit of a, this is maybe a little bit of a rough introduction into debugging. I think I could probably teach this a lot more thoroughly. I'm kind of doing this just a bit quick. But this should hopefully be enough to get you started. Don't be afraid to kind of play around with this. Super handy, especially, for the labs, it's kind of debatable because, the lab code is relatively simple. But I think once you start really implementing the next level of complexity, maybe for your ENEL 300 project, this is something that's really going to come in handy.